Greetings everyone and welcome back to the bench. First off, I want to say I really appreciate the interaction in the comments section. That does nudge me to think. Sometimes I just need a nudge. And I think I know what the problem is. I did one test. I haven't done anything to this amplifier yet, but I performed a test and I think I know what the problem is. But first, I want to explain what the problem is not and why I believe that. First off, it's nothing to do with the global negative feedback. Keep in mind that the oscillation is 40 megahertz. That is way beyond unity gain in pretty much any audio amplifier. That's way up there. That's a whole order of magnitude. So that signal is just not going to get passed around in the amplifier. So changing the gain by setting the feedback resistors different is not going to have an effect. That was a good idea. Somebody mentioned to change the gain and you can see if the signal is coming through the amplifier. And in some situations that is a good test to perform. Very good idea. And I did test that, and of course it didn't really it didn't do a single thing to the oscillation. It just stayed the same. Number two, it has nothing to do with the heat sink being attached. It's not, the amplifier is not picking up external noise. It's not a capacitive feedback from the output section to the input section. If it were, if I just put my hand on that, I would see a change. As a matter of fact, I can take a piece of wire, and I will turn this thing on and demonstrate that. I can take a piece of wire and touch the leads of resistors and other components around the circuit, and it doesn't change it at all. So it's not an issue where it's picking up signals from the air or feeding back through the air through like a capacitance or routing on the board or something like that, or insufficient shielding, things like that. It's definitely not that. So what is it then? What do I think it is? I think it's the output stage is oscillating. I performed a test by touching a couple ceramic resistors, one on the tab of the transistor, which is the collector, and the collector of this, the other on this heat sink. So the heat sink would act as like a common route for the the capacitor. It just acts like a big thick trace. It didn't get rid of it, but it did diminish that oscillation. So the problem is these transistors are very fast. The 2SC5200 and 2SA1943 have a data sheet rated bandwidth of 30 megahertz, which is an order of magnitude more than some older transistors that were used. So you have to be really careful. You have to have good layout. Even though this is a pretty small board, I'm running the supply rails from here. It goes over here through the thick wires over to the stars into the capacitor bank here. And at such a high frequency, these ceramic caps really need to be closer. And same on this side. It's not like I say, it's a very small board. You can see in comparison to my hand, it's not very big. But the speed of these transistors are a problem. At least I believe that's what the problem is. It's not totally tested yet. The nice thing, when I have boards professionally made, I can have nice flood-filled grounds, nice thick supply traces. I can orient the capacitor bank closer to the output stage. Put these ceramics over here closer, and I think I will alleviate the problem, but not totally. Another thing I need to do is put something called a base stopper resistor. If you work with tube amps, you probably heard of something called a grid stopper, or MOSFETs, a gate stopper. And what that does, it interacts with the capacitance to make a low-pass filter. It slows the device down so it doesn't oscillate. So it's kind of funny, we make these nice high-speed transistors for audio that we have to slow down because of the characteristics, and we have to be extra careful of their layout. So the layout on this board is just not good. If I tried slower transistors, this probably would work just fine. So what would be the value? Where do the base stoppers go? I've been reading up on it and looking around, and on a 2-transistor output stage, you have the driver and output. Sometimes you have triples where you have a pre-driver, driver, and output. But on an amplifier of this wattage, I think it's overkill. Of course, Bob Cordell, in his book, where he's reaching for extremely low distortion figures, he does use output triples. So the VAS stage doesn't have to deliver a lot of current. But for the 2-transistor stage here, where you just have a driver and output, the base stopper should go at this position. I've seen it in other positions. There's just not clear answers as to what people are saying. But as far as the value, it would be somewhere between 2 and 10 ohms. I think a value of 4.7 ohms would be a good value to put here. So if I do that and you have a better layout, I might try to try to bring a ground out here and then add some bypass caps near these transistors and see if that cleans it up. But first I'll do the stopper resistors, see if that helps. Here's the schematic. I changed it, altered it as the amp is right now. I drew these in lightly, these Miller caps. Not sure if I'm going to keep them. I'm not going to throw band-aids all over this amp if it's not needed, but they might end up staying, but I'll just show them here. And I also added that 1K resistor like I mentioned in the other video in this CCS up here in the VAS stage. Another comment was, what did I do to this amplifier after I had it actually playing music, and to that other video where I found the oscillation? The answer is nothing. I was running it on a lower supply, and the oscillation really doesn't affect the amplifier's sound. I mean, I can still play music through it. It's just that there's that high frequency oscillation going on. I mean, I did put it on the heatsink, and putting the heatsink on here did not have an effect. In fact, I tried grounding this heatsink. Right now it's floating because there's isolating screws, and these transistors are in the full plastic package. There's no metal on the back of them. They don't have to dissipate a lot of power. But the outputs have the isolating washers and mica insulators. Actually grounding this heatsink and looking at the output, it didn't change a thing. Why doesn't the output change when I have a load on it or when there's no load on it? It could be that at 4 megahertz these 4 ohm non-inductive resistors are still inductive. I mean, even the wires are quite inductive to to such a high frequency. And there still might be current flowing through the Bouguereau cell, the RC network on the output, which does still load the amplifier somewhat. So, well, that's my explanation. Okay, the amplifier is powered up again. And just to review the oscillation, it has these little packets. It's like modulated. It's a oscillation that's within an oscillation, kind of like. And as I turn this up, we're getting this high frequency oscillation, about 40 megahertz. See if I can stabilize that a little bit. 38, 39 megahertz. As I turn that down, you see they're in packets. Stabilize that. They're like in little pulse, like little packets where it grows stronger, grows weaker. I'm not sure why that's happening. But what I'm going to do, I'm going to hold on to this wire and touch components on the input stage. And it might, you might see a little spike because of the electrical noise. And you might see that wavering. That's just the 60 hertz electrical noise it's picking up. The underlying oscillation is just there. It's just riding on that waveform. You see that? The oscillation's there. It's just riding on the 60 hertz noise. And just touching different parts. Different leads. Here's the current source in the VAS stage. It changes slightly. Touching the lead on that 1K resistor. Touching leads on the bias spreader. Nothing much. If I touch, see, now I'm putting my fingertip on the leads of the output drivers. See how that changes? This is the tab of the output transistor. See, I'm getting this effect. That's why I kind of think that it's might be in the output stage. Now here's the amplifier playing some music. I have the horizontal and vertical turned down for audio range. That's why it doesn't look as bad. So yeah, I mean, it sounds fine. It's just, it's got that oscillation riding on it. So let's take a look at some waveforms here. Okay, here's my 1 kilohertz waveform. I mean, it has a nice waveform, nice symmetrical clipping, no weird oscillations at clipping. I mean, this waveform is thick because, if I turn this up, there's that, crank that up a little bit, there's that 40 megahertz oscillation on there. Here's what the distortion of the amp looks like. Of course, that's the 1 kilohertz fundamental. That's the 4.5 kilohertz pilot signal that I use to, just use it as a reference. It's 1% of this. So if we turn this up, there's just noise. There's no distortion in this amplifier at 1 kilohertz. At least what I can measure with this oscilloscope. That part of the amplifier is looking good. Of course, a 40 megahertz notch is not going to be displayed here because this only goes up to, whatever, 10 or whatever this goes out to, 5, 6, 7, 8, 9, 10, 11. So that part of the amp's looking good. I just need to get rid of this oscillation. Okay, so what I'm going to do is take these little ceramic capacitors and touch one on the tabs of the output transistors, the other end on the heatsink. That'll let the heatsink act as just a path across the supply rails. So in a way, it's kind of a supply bypass here. So here's the first one. That's on the negative transistor. Wait a minute, I'm not going here. Look at that. Still some oscillation, and now the positive side. Wow, that almost completely took care of it. I'm not getting a good connection, but yeah, that's real good. Real good. So yeah, I think it's the output stage, and it's a matter of better supply decoupling and putting the stopper resistors in the output stage, that just might clear it up. I'm going to have to actually try this. On the board, I don't know how I can really get a ground out to add the bypass caps, but I'll start with the stopper resistors and see if they do anything. Okay, the amp board is going under the cutters here. So yeah, this should be easy. Just cut this section of wire out, this section here, and solder in the 4.7 ohm stopper resistors. See what happens. Okay, I got them on the board. Where's my pointer at? Okay, so I soldered two 10 ohm resistors in parallel. There's one on this side. I was able to get one on the top side, wherever it is, right there. This thing's going to be a Frankenstein board by the time I'm done with it. So what that does is puts the, right there, the base stopper between the output and the driver, and one here. Hopefully I don't need any here. Like I said, I don't suspect I would, but I don't know. We'll see. So, will this make any difference? Let's power it up and see. Okay, here's what we got now. Now it's just a bar. Remember we had those pulsations? Now it's just a solid bar. Now if I turn this up, uh, 100 millivolts per division. So we have 1, 2, 3. A little less than 400 millivolts. And it's still at the, about 40 megahertz. So those have greatly diminished that. Now I'm going to put those capacitors on the output transistor tabs and touch it to the heat sink on each end. See if that knocks that out. Well, heck, I did one and it already knocked it out. Oh yeah, knocks it right out. I wonder if I try a smaller value. I wonder if I can go down in value. Yeah, it's such a high frequency, I would think it would. I have these 102s. These are just Mylar 102s. I had 0.22 ceramics before. So let's see what the Mylars do here. Yep, knocks it right out. Gotta get on there. Darn it, if I'm not holding it on worth a crap. Oh, flatlined it. Perfect. Knocked it out, man. Knocked it out. Yeah, so I think I got this problem licked. I'm sure there'll be more problems creep up as I test this thing, but the oscillation problem, putting in those stopper resistors and laying it out better. I want to see if I can run some grounds over here and put those capacitors in. Like I say, when I have boards professionally made, I can arrange so that the power supply bypass caps are closer to those outputs, and we shouldn't have to deal with this at all. There'll be less inductance in those power supply rail traces than I'm having on this board here. So yeah, it's just a combination of these fast transistors and the layout of the board which is doing this. So I can breathe a sigh of relief now, I think. At least for now, we got a lot of tests to go through. Well, now we got a cat up here on the bench. Wow. Snicker's brain waves, could those be causing the oscillation? Yeah, it's quite possible. The internet guru. I have to look, I don't remember his name. I think it was John something. The internet guru. That's Snicker's biggest fan, he says. Hey Snickers, you got a big fan, a big fan on the tubes. And he wants to sit in my lap. Yeah, I think Snickers was far away. I don't think it was his brain waves in this case causing any oscillations. Okay, so what I want to do here, I want to do the first power test on this thing, and then I'll wrap the video up. Off camera, I'm going to install the stabilizing caps. Hopefully I can run a ground and over here near the outputs and see if I can get rid of that last bit of oscillation and come back and go from there. But right now, let's do its first power test. So I cranked up my supply as high as it'll go, plus minus 32 volts. I turned the amps all the way up to 3.2. So that should be enough to power test this amp. Let's go ahead and start with the 4 ohm load and see what kind of power it makes. Now keep in mind that, like I say, this supply doesn't go as high as the amps rails are supposed to be, plus or minus 35 volts, or maybe a wee bit more, depending on the actual power transformer. But yeah, I just want to see what it can do. So, okay, so I'll turn on the output and crank it up. There's clipping. I'll bring it out of clipping, just so it's out of clipping. Getting 17.7 volts. Letting it run. Those little transistors are probably scorching hot. Before I do anything else though, I'm checking the bias. Oh yeah, that bias, it's falling right back in. Keep in mind these transistors are very hot. The heat's going to stay in them, unlike the TO264 I'm going to use on the board. So it might make the bias jump up a bit, but the bias is already fallen back into line here. So I am thrilled with the bias stability of this thing. Let's see, I got a 4 ohm load on the output, so 17.7 squared divided by 4 ohms. 78 watts, not bad. With the right supply, we should probably get 90, maybe 100 watts with 4 ohm loads on this thing. But if you remember, my objective was 50 watts with an 8 ohm load. So again, we are a little bit undervolted on the supply, but I still want to see what it can do. Okay, let's look at the 8 ohm load now and see what kind of power we get. So we'll take it up. There's clipping. Have to look at the clipping characteristics. Make sure it's 20 volts. Can't really get any higher. 20.1. We'll just say 20 volts. So that's well, that's 400 divided by 8. 50 watts. So we hit 50 watts even at the reduced voltage. So with the proper supply, should be able to do a lot better. Maybe get 60 watts. So I would say that that objective has been met as far as output power. We wanted 50 watts, and we should be able to get that for sure. While I was at it, I checked some bias currents, see how the amp was running. I'll have to go watch the old videos and see what the designs were, but the input stage is running at 1.2. I think that's what it was designed to do. The voltage amplification stage is running at 6.2, I believe it was when I measured it. So slightly less, but still that's in the ballpark. Of course, I have the output bias set to around 40 milliamps. So the amplifier seems to be working just fine. Like I say, I will have to take care of that oscillation, hopefully for good. But we still got to get through a bunch of other tests. We have to get through step response and distortion tests. So is this thing going to stay stable, especially with a step response test when I load the output with 4 ohms and put a capacitor across the output like I did with the LM1875. That LM1875 on those little boards performed just gorgeous step response tests. Will this amplifier here do as well? I'm suspecting, because of this board and the issues with the supply rails to the outputs, I suspect we might see something until I actually make up some boards, have boards professionally made. You know, that would probably take care of that. So good, onward and ever upward. Thanks for watching.